So I magnify the mode. This is a profile likelihood, and this is posterior samples of the time delay. And the vertical red line represents the true time delay. And this numerical summary shows that we are catching the truth within one posterior standard deviation. However, at the time, we didn't know whether our estimate was likely or not. So we visually check our methods, our estimates by shifting the blue time series using our estimates shifting estimates shifting in x and y axis. So it seems like our estimates are very likely because their fluctuation patterns are very similar, given our estimates. So let me explain another phenomenon, microlensing, because this is very common in real data set. The microlensing effect occurs when stars inside the lensing galaxy introduce some flickering noises into the path of the light. For example, if there is a small star near the path, then that star may behave like a small lens, affecting the lensing magnification. If the time scale of that microlensing effect is much larger than the time scale of the intrinsic variability, then the two time series may show you some polynomial long-term trends. So for example, in this data set, you can see the two time series have different linear trends because of the microlensing. As you can see, the short-term variabilities are very similar. But just because of microlensing, it has some different trends. Then how do we model this? The common way is to fit a linear regression on each time series to remove the long-term trends. Polynomial, but here is linear. But our method is a little different because we are accounting for the difference between the long-term trends. For example, we are accounting for the capital Y minus capital X by the polynomial regression. So the advantage is that if you use the popular method, then you need 4 parameters: intercept, slope for each time series. So there are 4 parameters. But if we use our model, then we just need 2 parameters: the intercept and slope for the difference between 2 long-term trends. So it seems like we are setting the time series A as a tilted x-axis, and we are feeding regression on the time series B so that it has the same slope of the time series A. So we reduce the number of parameters in the model. It's just half. And we fit our model on this data set, on the previous data set, and we also obtain a dominant mode of the wide range of the time delay. And we ran our Bayesian method near that time delay estimate. So I magnified that mode, and I superimposed the profile likelihood curve over the posterior samples of the time delay. And this time we are catching the truth within 2 posterior standard deviations because chi is less than 2. And we also check our estimate by adjusting the time series B. So it seems like fluctuation patterns are very similar, meaning that our estimates are very likely if we don't know the truth. So I also prepared a real data example, which is for Quasar Z1029 plus 2623. This quasar is known to have the second largest time delay. We ran our model, obtaining profile likelihood, running our Bayesian method, and magnify the mode. And we also check our estimate, the posterior mean, by adjusting the time series B. Seems like they are reasonable. But in real data, we don't know the truth. I also summarized some previous estimates from several astrophysicists, and it turns out that their estimates are very vague, considering that their interval estimate is large, very large. So you may wonder whether our method is overconfident. I mean, are you overconfident about your estimate? Isn't it too much confident? But considering that considering the time delay challenge as our calibration, I mean, here we achieve the best precision achieving the targeted accuracy. I think our method is not overconfident. I mean, based on this blind competition. I think, what time is it? Okay, 2 minutes. Okay, currently, the organizers of the time delay challenge are about to launch the second time delay challenge, which is another blind competition. And this time they will provide multi-filter light curves, the R band, G band, V band, I band, etc., for the same time delay, for the same system. So it's kind of analyzing vector time series instead of scalar time series that I have shown you. So this time, they will evaluate how accurately we estimate the Hubble constant. I mean, of course, we will estimate the time delay, but we are not reporting the time delay estimates. We have to submit our Hubble constant estimates for the blinded Hubble constants. And yeah, hopefully, I will also challenge this blind competition again, and I hope we can achieve something nice. Thank you very much.
So you said the Bayesian method can get stuck in one region of solution space. And when you got multimodal solutions, it can get stuck. And your method is better, at least for multimodal along this one parameter. But the examples you showed were all single solution, right? Because the probability was just peaking at one place. So were there any examples among the 5,000 that you did for the challenge where there were two time delays that looked equally probable? And what did your method do in those cases?
Okay, this is a very good question. Your question was about whether there are some cases for some multimodality. I chose these examples to show some typical picture of our method. But in reality, even in time delay challenge, there was some multimodal posterior distribution. And actually that happens when we fit a curve shifting model on the data set suffering from microlensing. For example, if you feed a curve shifting model on this data set, for any time delay, the fluctuation patterns never overlap because it has different long-term trends. So in that case, the most likely time delay value will be at the end of each tips, because at each tip, it is possible that there are no, the only part that makes the light curve connecting very well. So in that case, usually what happens is that the mode will occur at the end of each tips of the time delay. So the mode will appear on both sides. I mean, that time delay will dominate this true mode because for any true time delay, it has different slope, which is very unlikely signal. So in that case, by applying for this microlensing effect, by applying this microlensing model, we can remove that kind of mismatch of long-term trends. In that case, if we run our microlensing model, then the modes near both margins disappear, and the true signal appears. Okay. That's how we account for that multimodal posterior.
But you never had a case where you had two equally probable time delays in the middle, away from the end?
Oh, that's a good question. I haven't seen any modes very close to each other near the true time delay. Okay. It is either both ends or true time delay.
But that means then probably the Bayesian method would be equally good, right? You'll never get stuck.
Before we come up with this microlensing model,
yeah.
we were stuck. we were stuck at local modes. We didn't know how to handle it. But it turned out that the reason that happened, the multimodality happened, was microlensing.
This
effect.
Now that you have allowed
now I adjust. So we solved that multimodality by some background science, not statistical multimodal sampling.
I see. Okay, good.
Any other questions?
So
wouldn't the same situation would happen if the source is somewhat periodic? Then you could have a sort of equally probable shift happening. I mean, quasar will not be like that.
Of course. If we assume that it has some periodic fluctuation patterns, of course the mode will be periodic again for each period, right? But quasar light curve is not that periodic, it's stochastic. So for this purpose, I don't think that will happen.
So is it easy to implement some periodicity in your method for some other applications, do you think?
This model is developed for to account for stochastic variability, but if you want to account for some non-stochastic time series data, then of course there are many ways to fit that periodic patterns, like sine curves or mixture of them, kind of.
So it will just introduce more parameters in the
Yes.
model. Good, thank you.
Yes, thank you. Any other questions?
Okay, so if there are no more questions, let's thank Tak for the very clear talk.
Yes? Okay. All right, I'll hold it then. Okay, so this will be an astro statistics talk in the very loosest sense of the word. There's going to be a lot of pictures and movies, so it'll be a nice little aperitif before lunch after all of that math. So this is sort of a more philosophical question about how do we actually access our data when you have a gigantic data cube or a large simulation. And it's a little bit more about how we can start to use intuitive 3D tools coupled with actual statistics and use those things a little bit more intuitively. And so there, and look, it's a plot with data, so that's my astrophysics right there. So when I gave a version of this talk to a mostly computational science audience, I had to sort of explain what an astrophysical simulator does. But I think this is a useful thing, a useful plot to have just to sort of center what our thinking. So you know, when you do a computational simulation, you have to pick a physics code, so adaptive mesh refinement or smooth particle hydrodynamics, something like that. And then you add in your physical processes that you think are important. So the things I do, we use prescriptions for how stars form, supernova feedback, and cosmological simulation, things like that. Then you send it to a supercomputer and you wait. Then you make some analysis and visualization plots. And then you sort of lather, rinse, repeat, right? You're going to do that a lot. Hopefully you don't have to go all the way back to the beginning and pick a different code, but you're going to iterate a bunch on tweaking your physics models and sending it to a computer. And then maybe, let's see, I don't know if the screen goes down a little bit more.
The resolution is set to the wrong.
Is it?
Yeah.
Okay, let's try that. Otherwise it's not a huge deal. So, go back.
Yeah, and I can give a very short introduction about our second speaker if you haven't met her already. And she's our very own Jill Naiman, and she's now an SF and ITC postdoc fellow here. And she's an expert on the simulation of small galaxies and star clusters. Okay, let's continue.
All right, cool. And so, yeah. So then you maybe would, after you visualize and analyze things, you could make a super cool movie if you want to. And here's just some examples. So again, there's that. This is a phase space diagram that I'll talk a little bit more about later on. And there's also, a slice plot, which I will also talk about a little bit later on, what those things mean as part of your visualization analysis tool set. So there's a bunch of different software that are either developed or under development. These ones are sort of already standards that people use. So there's often various problems that people come up with when they start using these. So one is that sometimes they're proprietary, which in science is not always what everybody wants. Others have user interfaces that sometimes people argue about. And this is a very loaded comment about Visit, by the way. So some people really love Visit. I haven't met a lot of those people. I'm gonna get, oh gosh, this is on the web too. Okay, I'm gonna get a lot of email. Anyway, and then things like Vapor are also great, but you might want to export in a format that other 3D software can use, and sometimes that's a little bit hard. So, okie. So I'm going to talk about stuff that I've been doing with a project called Astro Blend. And basically, it's a visualization and analysis package aimed at large data sets. So this is very biased towards computational stuff, but you can also, in principle, use this with observed data. And it's built with a YT backend. And if you want the nitty-gritty details, I think it's actually out and published now. There's a paper in astronomy and computing, so you can check that out. Okay, so I said all those things, and that you should be impressed that it has a YT backend, but maybe you don't even know what YT is. So let's get into that. So this is just a snapshot from the YT website, and basically just says YT is a Python package for analyzing and visualizing volumetric multi-resolution data from astrophysical simulations, radio telescopes, and emerging interdisciplinary community. Whew, okay. So what that basically means is you have, it gives you a pathway to analyze data in a variety of ways. So this is all plots from an isolated galaxy simulation. So it's just, I think it's ENSO simulation. Somebody wanted to, make just an isolated sort of test galaxy. And so in the upper part there, it might be a little bit hard to see, but this is a 3D representation of some streamlines. So you can kind of see gas falling in and then starting to circle around this galaxy. Below that, there is, again, that slice plot. So basically, they're just taking a slice of the volume centered on the galaxy that is formed. So it's X and Y are the coordinates, and then it's colored by density. So you can start to see the spiral arms form. You can also do a cool volumetric rendering. You can also make movies. And then the more sort of analysis stuff you can do is, again, you can plot two different variables and look at how much of your simulation volume or how much of your simulation in mass is at those specific variables. So this is temperature is on the Y and density is on the X in case you can't read. And the colors are the cell mass. So, from looking at this plot, you can say, oh, I've got a lot of cell mass that has sort of these high densities and sort of intermediate temperatures, but I also have a population that has higher temperatures and is more diffuse. So you can start to do some more serious analysis that way. Another thing that I added, more on the visualization side, is you can export isosurfaces in an OBJ formatting. So what does all that mean? So basically, you can visualize your simulation in a different way. So this is a typical slice plot. This is a student of mine. She was simulating the complex red giant branch stellar wind structure in M15. So basically we put about 50 stars, mass-losing stars, in an M15-like gravitational potential and wanted to know, okay, these things have different winds based on where they are on the RGB, on the red giant branch, and how do those winds interact with each other? What is the overall hot content, cold content of this star cluster? And so you can just take a size plot of your simulation. You can see there's sort of one star up there that is losing a lot of mass. There's these interesting shocks that are forming of more hot material. So you can definitely, make a cool plot like that. But another way to look at this data is to do a few ISO density contours. So these are colored by temperature, where blue is colder. And so sort of at higher densities on this side, you are basically just probing the structure right around the individual stars, so you can see how your individual stars are distributed in this cluster. As you go to lower and lower densities, you can start to see the shock structures start to form. And as you have this sort of lowest density material, you're at the cluster radius, and you can see that you're going to have coming out of this cluster some material that's quite cold from this large cold mass-losing star. But you're also going to have all of this hot shocked material, and so you're going to have these different components coming out of your cluster. So that's all well and good, but you can also do some fun stuff with it. So this is a way of just quickly checking out your surface that you've made. So this is in a program called MeshLab. So when you export in an OBJ format from YT, you can just upload them into MeshLab, and then you can look around in in a 3D space. And so this is just an easy way to look at things. I'm going to speed up this movie a little bit. And so the point being, you can also upload multiple surfaces, and then you can start to see, shells around shells, how the shock structure is interacting at these different densities. Another fun thing you can do is actually upload this onto the web. So this is a website called Sketchfab, and so it's mainly meant for people that make 3D models in an artistic sense, but you can also put your scientific models up there. And you can do cool things like annotate your scientific models. So I've got, so you can basically just click on your model, you add a little description, and it tells you something about what's going on. I've uploaded a few more models. If you want to just check out sketchfab.com, Naiman. They've actually added a feature where you can do animation. So there are some tests of that, some test particles for a globular cluster-like simulation that's actually evolving in time that you can interact with in 3D. There's also a galaxy merger simulation that's got, I think, 1 billion particles, so you can do these complex, high-resolution things. Also, you can just go inside your simulation and look around, which is kind of fun. You can also, if you want to, there's someone here, I forget exactly who, that actually has a 3D printer, so you can 3D print your simulations. And usually when I talk about this, I have my little 3D printed thing in red, but I forgot it at home, so I'm sorry. But the other one that I'm showing here is from James Guillochon, so if you contact him, he will happily show you his cool 3D printed thing from some tidal disruption debris. And his is bigger than mine, so why would you want to do this? Because you can have something on your desk. You could also give them out at public lectures. People are starting to use these as visualizations for people that are visually impaired. All kinds of things. You can also put them on 3D websites and just let other people print them out if they want. So now I'm going to talk a little bit more detail about stuff that I've been doing, specifically AstroBlend. And so these are just a few example visualizations you can do with either AMR or SPH data. You can also annotate your simulations. So these are some examples of, instead of looking at a plot of streamlines, you can actually do interactive simulations with arrows and things like that are showing you. This is showing sort of a disk around a supermassive black hole, or the particles of gas around a supermassive black hole. So AstroBlend is built into Blender. It's a Python library for Blender. So what the heck is Blender? The short version is it's basically a visualization and 3D animation tool used by people that do that sort of thing. So I said that it's sort of a free version of Maya, but that's not entirely true. But Maya is what Pixar uses, so it's sort of in the same vein. And these are some of the things that Blender is typically used for. So making really cool illustrations or doing cool 3D models and making movies. So what's nice about it? Well, it's open source and it's free. That's great. It's also got a Python API. There are a few other astronomers that have started to use it, and other scientists as well. You can so in its 3D. Well, I'll show some pictures, but it's got a 3D interactivity in which you can combine data from multiple simulations. You can easily script complex camera motions, and again, there's direct data access with YT. So here's just a table of what kind of data you can use now in AstroBlend. But this is being updated sort of when I get around to it. So I would say check the AstroBlend website, just astroblend.com, to see an updated version of this. So this is what Blender typically looks like. So you've got your 3D view where you can interact with your models in a 3D space. You've got a text editor where you can write in either programs there or call external Python programs. You've got a Python console, and then you can do quick renders in your image viewer. So here's just a really quick render. You've got a cube, it's being lit from behind, and your camera is sort of in front of it, so that's sort of what you would get from your render. So here is a simple Python AstroBlend script that you could run in Blender. So first you just import the library. I call it science because I can, and I think it's funny. Then you can load your object. In this case, these are some OBJ services that I pre-generated with YT. Then you set up the lighting, so I'm deleting the cube and the lamp that was there before. I'm saying that I want the lighting in my image to be from the surface itself. Position the camera, say I'm going to render my image to this directory, and then render. And this is what you get. So this is actually that isolated galaxy. It's the gas structure right around the sort of central disk. And you can see that there are certain sections that are a little bit glowier, they're different colors. And those are sort of described by, in this direct interaction with the data. So this is another version of Astro Blend. It creates the same image, but you're actually interacting with the ENSO data directly. And you can actually download this ENSO data if you really want to. So you say I want 2 isodensity contours at these various densities. I'm going to make one a little bit less, or a little bit more transparent than the other. I want to make the emissivity proportional to Bremsstrahlung. And then you use the same load command, but with slightly different parameters. And basically load can figure out what you're trying to do. If you're trying to access an OBJ file that you've pre-generated, or a text file, or in this case, directly with the data. And so this is more technical for people that actually know YT. This is what YT does versus what Blender is actually doing. So YT is actually querying the data and calculating all of the emissivities and colors and things like that. And again, load can figure out what you're trying to do. So here is a movie that I can never figure out where to put in, but it's really pretty, so we'll just show it now. So this is, again, a few billion particles. This is a galaxy merger simulation. If you want to play with one of the snapshots of this on the web, it's on my Sketchfab. And this was actually with text formatting output, so you can output any SPH data as this and make movies like this. You can also annotate your simulation, so you can put in text, you can put in arrows, you can put in simple spheres. I've also got an example on the Sketchfab that shows the 3D structure, I think in correct units, of a few dwarf galaxies and also globular clusters surrounding our Milky Way, so you can do that. You can also do complex camera motions. So here is just an example where I have something fixed and I'm rotating and zooming. You can also just give it a set of points and a set of pointings for your camera, and it will interpolate between those points. So you can do things like that. And again, it's just one function call, so it sort of simplifies all of that. Okay, so right now I've shown you a lot of cool visualizations, but how do you start to actually interact with your data in 3D? So here, this is in the dev version. This is in the paper, but here I'm actually using the GUI to go directly to my gadget data and uploading the data into Blender. So it's giving you a little outline cube of where your data is. And here I can start generating some of those visualization, but also analysis plots directly in Blender. So here I'm generating an isodensity contour, so it should look a little familiar when it pops up. And you can change, what you're coloring things by, the emissivity, what your isodensity is, those things. And so there's that little isodensity contour again. But on top of that, I can start to do some analysis plots. So this is an example of doing a slice plot. And again, this will be generated in the 3D space. Here I'm just selecting a color. Boom. So your slice plot shows up in the 3D space, and then a more sort of analysis-y version shows up in the image viewer. And so now I have both a sort of visualization thing overlaid with a more analysis type plot, right? So these two things can start to mesh together. You can also actually move your slice plot and interact with it in 3D. So maybe you want to take something like an off-axis slice plot. Maybe you want to move the location of your slice plot to part of the 3D space that looks interesting. You can also do that in an interactive way. So that's just what this is showing. So this, I'm just doing something not that interesting. I'm just sort of tilting my slice plot, but you can move it and make it have all kinds of weird orientations. You can also do projection plots the same way, so that instead of taking a slice, you're actually collapsing everything. The interface is very similar, so I'm not going to show that. So that's just showing that you get this sort of off-axis type thing. And next, I think we go to, so same interface for the projection plot. So you can also start to do things like phase plots also in 3D. So the way that YT is set up is you specify a radius of your data cube and look at the parameters within that radius. So you can, in 3D, select that radius in the 3D viewer. So you start off with some default sized sphere. So now I'm shrinking it. And when I shrink it, my phase plot changes because now I'm selecting a smaller slice. And then you can actually just move it around and select different parts of your data cube right in the 3D space. So if you made some, if you made some isodensity contour and it popped up somewhere not in the center, you could just move your phase plot over there and say, oh, that might be an interesting thing to look at. You can also look at your grid structure, which is another way to figure out where you think the most interesting things would be. So it's most refined at the center, probably the most interesting stuff is happening there. Finally, this is just a quick demonstration of how you can overlay multiple data sets. So again, this is data that was generated with a completely different code and completely different units, and it can upload it and scale it and put it where it should be in the physical space. And so this will just show you, I think it zooms in on a little particle cloud. I can sort of move through that. Yeah. So now I'm just flipping around. And so this is the particle cloud from that second simulation. And so you can plot both things in the same space and interact with them in 3D in the same space. Even more dev version. So hopefully that one, the interaction with the data in the GUI will be pushed soon. But an even more dev thing is you can also start to do some simple volume renderings and make those interactive. So here's that same isolated galaxy. In this case, I uploaded it into a volume rendering cube. And let's see. Oh, this is pretty quick. Right, so you can play with the transmission of your volume. And this might be like an interesting way to first start looking at your data, right? You can just be like, I don't know what's going on. I'm just going to plot this up. Oh, there's something kind of interesting at the center. Maybe I should, take a phase plot at the center, or try and do a slice there or something like that. So there's a lot of things that need to be worked on. This punchline of this is basically there's very simple transfer functions to make your volume renderings already in Blender, but we can put the YT ones in and make them a little bit more physically realistic. So I wanted to mention a few other people doing things in Blender before I go on to just some cool gratuitous movies. So there's people doing visualization in Blender. So Miguel Aragon has some really cool stuff. You can check out his website. Also, Brian Kent just had a book aimed at how you do more like physically based models in Blender. So if anybody wants to do more of that, I would suggest checking out his stuff. Also, Dr. Taylor, whose first name I cannot pronounce, so sorry about that. But he's also done some cool volume rendering in an older version of Blender. So he's also a really good resource for this type of stuff. Also, I want to mention Glue, which is another project that people are working on here. So they've started from observational data cubes, but they're also going into simulated data. So here's just an example of their interface. So you can upload a data cube, you can sort of move through it. I think this is just in Z. Again, I'm not an expert on this, so this is here if you have questions about it. But you can also do interactive plots, so you can select regions, you can also take cool slices of regions and do plots based on unwrapping your data. So that's what this is showing. Presumably that's a galaxy, and you're just unwrapping your data cube along those along the lines that you've drawn, which is what they're going to pop up next, right? And so then you can also peruse your data that way. They've also started to do some interactivity in the 3D space as well. So here's just a quick example of how you can select regions of your 3D space. So presumably once you've selected a region, you can do data analysis on that. You can say, you know, what's the phase plot of this, or you know, what is my average gas temperature, or what have you. So this is another thing that they're working on that's being worked on here as well. Okay, so now some gratuitous movies in the last little bit here. So this is not mine, this is again Miguel Aragon's, but he's actually done some really cool things with interactive visualizations, where he's got a Connect set up, so you can actually sort of like zoom in this thing with your hands. So he's doing a pseudo volume rendering, so it's a bunch of isodensity surfaces. And then you can also see the streamlines of particles, and I think he's going between gas temperature and density when he clicks between the two different things, but I'm not entirely sure. Or maybe he's just turning off one of them. Anyway, so that's kind of a cool thing that you can do. This is sort of the first test run of AstroBlend that I did. So this is combining artistic models with actual data. And that's a sky image that is not to scale, but everything else I think is to scale. So this is a fake galaxy. I basically just Googled galaxy model, and someone had made a free version of this. So here is sort of some of the positions of the dwarf toroidal galaxies. Again, on Sketchfab, I've got those, and also the globular clusters. This is how they're moving. And then I've actually done a simulation of how the gas, we expect some of the gas to be in a Fornax-like thing, so I thought I would overplot that on the actual position of where Fornax is. So what you're seeing here is the inner part is gas that's sort of forming a disk as this dwarf galaxy is rotating, but it's also, this dwarf galaxy potential is moving through the background medium, and so you have some little bow shock forming. And so that's what the outer structure is. And so you can sort of see the disk evolve. Someone told me it looks like a tadpole though, so so the tadpole forming. Right, and so everything is to scale in this. So potentially you could also put this model on the web, and then people could play with the actual thing in 3D. And again, this is just some annotations, and so that's just a really simple, easy test run of how you can combine all of these things together. And then I was going to show some Sketchfab awesomeness, but I don't think the internet is working, so again, I would just say go to Sketchfab /J Naiman and check those out. So thanks so much.
Thank you for the great talk. Questions?
Sorry.
Go ahead.
So the simulations that you showed, I mean, there's no uncertainty. I mean, everything is perfectly known. But in real data, I mean, you do have to account for variance and all sorts of fuzziness. Is there provisions in Astro Blend and or YT that lets you do, they include that sort of thing?
Yeah, that's a very good question I do not know the answer to. I presumably in Glue, Melissa,
yes. Yes,
they have some
yes.
I know that there is some of that in YT. I have never used any of it, so I have not implemented any of it in Astro Blend. But that is certainly something that is a good question to hear, because then I know that people are interested in that kind of thing. So,
yeah, I mean, the way that a lot of that can be implemented in Glue is that it's attached to Python directly, and so anything that you can use in Python, you can just add in.
yeah, that's a good point. So, I mean, there's a Python console in Blender, so you can access your data just like how you would access it, with any Python console. So, yeah. But I mean, presumably there'd be cool ways to sort of show that.
Yeah, we're working on error bars and
Yeah.
fuzziness, and it's on the list. But for now, you can use stuff that other people have done by Glue has this concept of widgets, where you can build your own little widget, and so your instance of Glue can have stuff added to it, and so you can use, like if you're specifically interested in that, you can use whatever your Python favorite is for that. Add it.
Yeah, I just haven't implemented anything like that yet. But I'm curious to see what you guys do, and I'll just
working
on it.
So in the CAD/CAM world, there are a lot of different kinds of 3D model things. Are there interfaces like for SolidWorks into blend?
Yeah, I mean, so you can, you could upload, I'm trying to think of everything it supports. There's a bunch of different 3D file formats. So the one that I'm most familiar with is OBJ, but you can do animations you can upload to like FBX, I think is an acronym. So there's a whole bunch of supported ones that are native to Blender. In addition, people also write a lot of converters. So if anybody has wanted to use it in like a visualization, then there's probably a formatting for it. So yeah, you can upload anything, I think.
How easy are those software to run in a laptop?
Yeah, I mean, so everything that I was showing, I ran on the laptop. I did edit out some of the loading time because like the surface generation, that kind of thing, are not optimized yet. So it's something we're certainly working on. So there was probably a lag time of about 15 seconds in actually generating the surface. But that is actually something that we're working on changing. The volume rendering, that was actually pretty quick. But when you get to larger data sets, it becomes a little bit of a problem, but yeah. Mm-hmm.
So you showed all of these are 3D grids based on position mostly, but sometimes you might want to look at like a phase plotted position and do that in 3D. Can you load other coordinates? How does that work?
Yeah, I mean, I don't see any reason why you couldn't. I just haven't. But yeah, I mean, the 3D space could represent anything, right? So you could do everything in velocity coordinates. I mean, I don't think there's anything that's stopping somebody from doing that. I should be taking notes. These are all really good ideas. There's fuzziness of data and doing things in different 3D coordinates. Okay, that's good. Got two things.
So going back, one question. You said maybe a problem for large data set. What's large?
Yeah, I'm trying to think. So the one that I was showing was, I think those files are maybe, I've loaded things that were about a gig for a snapshot, a gig or two. So the surfaces for the globular cluster model, those snapshot files are around a gig or two. Doing an interactive volume rendering of that is not possible at the moment because the way you have to do it is you have to map everything to a uniform grid. So we're working on ways to sort of have Blender be able to render a AMR grid, and so then that would sort of get past some of those problems. But yeah.
What about unstructured grids? Would that be a feasible future module?
Yeah, so YT I think now has unstructured grids supported. So I mean, since this is just using YT as like a data loader, I mean, once you have it in the YT formatting, then you could totally do it. I say having not tried it, but.
So if there are no more, okay.
Hi, Joe.
Hey.
What's doing the volume rendering here? Is it YT or is it something else?
It's the Blender native
Okay.
volume render.
Okay.
So that's one thing that we're thinking about. Maybe we could put some kind of version of the YT volume render in here because that can do AMR. But
Yeah, and we're going to have OpenGL volume rendering.
Oh, sweet.
Yeah.
Okay, good to know.
Okay, so now let's thank our two speakers.
Harvard University.
Well, I don't think so.
Hi, my name is Trey Winter. I'm an astrophysicist in the solar physics group. I've been doing a series of video wall displays at different places. I'm doing lots of data visualization. I'm going to invite you to a meeting where building a new video wall and all about the library. And I'd like for you to be part of the initial use case plan. So because I love but also too, I would like to talk to you about because I'm working on doing my solar and making those printed models for a museum for the blind. I'm doing a video projection on it. And I was looking at ways to actually take my 2D images and actually build that into 3D print books. It seems like a lot of So I would rather write you on for that's something you'd be interested in. Yeah, so I've got museum connections. I've been doing like museum exhibits for a while. I've got a bunch of museum exhibits and they would all love to have more inclusive stuff, but they just don't know how to do it. So there's an NSF opportunity coming up for inclusive stuff. Yeah, I can't believe we haven't met yet. So I'm all about the data visualization. I'm trying to get people talking more through the library. Yes. Yeah, well. Yeah, well, no, I'm trying to get so I work a lot with the library, and we're really trying to make. We've got so much talent. Alyssa and all that stuff that she's doing to illustrate. Yeah. And John Zuman and all these people. I'm almost not doing actual science anymore because there's so much work to be done in the visualization. Yeah, me as well. It's a niche that is underfilled at the moment, and it is very important. There's so many different ways you can go with it. And right now I'm going into the museum space with it, but that's not the only space that you can fill. And what I'm working on doing with the rest of the library is trying to use it to connect all these different groups. So that's like, well, you're doing this thing, it could, and it can be used here in this other one. Try to get those synergies happening. That's kind of hard. Alyssa's over at 60, and John's over at the CXC, and people have a lot of talks to each other. But I'm really excited about doing the 3D printing as well because I've worked with there's a blind astronomer who works here every now and then, which amazes me. Do you know her? Do you know Wanda? Yeah. So you know Nick Murphy? Yeah. Okay, so I'm working with him. Yeah. So anyway, I'm very much trying to get this astronomy and trying to get away from trying to get away from data visualizations, but data expression, so that we can maybe think about. Wanda was trying to work on sonification, and I don't know how that would work for my solar data, but feeling tactile would work. So, 3D printers are cheap and everywhere. Like a standard template for an exhibit. We'll build one for a local museum and then put everything free on the web so that a museum can build their own. Yeah, so if that sounds exciting to you, we'll start talking about it. You'll get an email today about the video wall. Yeah, it's going to be an LED wall. Oh, the Arduino's tile. Yeah. So you need to visit my solar lab downstairs. We've got a nice 9-panel wall that's. Yeah. Well, no. The Arduino wall is actually pretty cool. I've seen one built with Arduinos. I've seen one built with Raspberry Pis, and that actually brings down the cost so much. But I haven't actually built one. I mean, I build a lot of low-priced ones for the museums that do nothing but play movies, right? And there are cards now that you can actually get for less than the cost of the Arduino 016 screens. Yeah.
I haven't like I just had
Well, the 3D stuff, I'm actually buying some commercial cards for the gaming industry. So much of cards, but they still cost about $3K a piece. So for 6 screens, but yeah, but it's actually so much better than it was. Well, it used to be that a thing to do the same thing was a $15,000 optics box, and when I built the one downstairs, which